Welcome to my presentation of the second ICSOBA virtual conference. The subject of my presentation is the two-step preheating of new anode with anode but wasted heat. It's a paper I did in collaboration with Alton Tabereaux, and it is a follow-up of the presentation done this year at the TMS. So I will introduce the subject and then I will present 3 different cases, summarize those results and conclude. So the introduction, we want to, for let's say the last 10 years at least, we are trying to assess a way to reduce the energy requirement of the cell and also reduce the impact of introducing new anode, coal anode in the cell on the stability of the cell. So we want to take advantage of the wasted heat of the anode, but try to preheat new anodes. So that's an idea that is floating. And there's some pattern, there's some work has been done, measurement. And then this year at the TMS with collaboration of Christian and Anode, we presented a paper where we are trying to preheat directly a new anode with direct contact with an anode butt. And this configuration is working well, at least in modeling part of it. But on the practical side, this would be challenging. So we are trying to here assess another new way to achieve the same goal. And that new way is a 2-step process. So in the first step, there's a box, a well-insulated box. We put in the bottom of that box a plate of metal or a more thicker block of metal, and then we put on it the anode butt coming from the pot. And then we let that in that first step, we let the system reach equilibrium. And in the second step, we remove the butt eventually. And then at the right timing, we put a new anode, coal anode, in that same box in contact with the preheated plate of metal or block of metal. And then we wait for the right amount of time to achieve the maximum bottom surface temperature of the new anode, and then we put the anode, that preheated anode, in the pot. So we will study 3 cases. And the first case here, it is a block of cast iron that we are putting on the insulating box, and then the number, the 225, is the conductor, the interface conductivity. The 225 was measured in the lab. So that's the number that is being used in that first series of modeling. So the idea is the first step is to wait 4 hours for the butt to preheat the block of cast iron, and then that it is initially at the room temperature. And after 4 hours, the system reaches equilibrium, and then eventually, when it's time to change the anode, you have to 4 hours in advance, you put a new coal anode into the box, and you wait 4 hours for that second phase to take place. So here I'm going to present the result for that first cycle, and then I will explain later what is a cycle. So initially, the block of cast iron is at room temperature, so 20 degrees. The anode butt is coming from the pot. And then that's the initial configuration of that system. And then after 4 hours of contact, the block of cast iron has reached this temperature around 350. And then the next step is to put the new anode, coal anode, in contact with that block, preheated block of cast iron. So that's the initial temperature of the second step. So we have the new anode. The system is upside down here, so the new anode is below. So it's the opposite direction. You would be in a real situation. So it was more convenient for the modeling, and it's also convenient for the showing the results. So you have to imagine that you're looking at this system upside down. So that's the bottom of the box with the preheated block of cast iron, and that's the new anode that you put it on top of it, and then that's the initial temperature of the system. After 4 hours, that's the temperature of the new anode. So it is about 240, and that's the first cycle is finished. And that's the temperature of the block of cast iron after those 4 hours. So it's no longer 20 degrees. It's 250. So that's why it wants to repeat that cycle a second time. So you preheat a new anode. So with the new, so you put a new butt now in contact with that block of cast iron. Now you're not starting, the block is not starting at 20, now it's starting at 250. So it will reach higher temperature. So if you repeat many cycles, you're gonna achieve a total steady state solution. But here what I have done is that I've done a total 8 cycles. The first 4, I waited 4 hours in the second part. And then the remaining 3, I only waited 40 minutes to put the new anode in the pot. And then by doing that, I achieved different solution. I will show what the difference is. So here, so the first 5, I'm waiting 4 hours before putting the new preheated anode in the pot. And here, from that point on, I'm only waiting 40 minutes. So the cycle was reaching its first part of the cycle here. We were reaching equilibrium about 400 degrees for the block. But now that we are waiting less time, the block is exchange less heat with the new anode, so it will gradually reach another steady state, pseudo steady state condition at higher temperature, close to 600 degrees. Okay, so now I'm going to present the solution of the last cycle after. So only waiting 40 minutes for the second part. So, and what happened is that the bottom face of the new anode is after that 8 cycle is reaching 500 degrees. So that's the final temperature of the new anode after 40 minutes of exchange for that last cycle. Okay, then new case. Now I'm replacing the block of cast iron by a block of copper. So it's a different material, but except that's the only change, except that they also I've replaced the thermal conductivity of the interface. Now I'm putting speculating that if I'm adding a film of liquid aluminum at that interface between the two materials, in the first part, in the first step, it is with the butt, in the second step with the new anode. Now, instead of having a dry contact, I'm putting a liquid film of aluminum, and I'm speculating that the conductivity of the contact increased to 800 watt per meter square degree Celsius. That have a big influence on what's the rate of exchange of heat. So now I'm starting cycles again with this configuration, but instead of starting at 20 degree initial for my first cycle, I'm assuming a temperature for the first cycle, I use 660. And after 4 cycles, I stayed around the same, so 674. So that's why now I'm presenting the less solution for that 4th cycle. And then with that very high conductivity of the interface, I'm reaching 616 for my bottom phase temperature. So this is the solution. So this is the initial configuration. So the anode butt in contact with the plate, a block of copper. So the block of copper is at 674. This is the temperature of the block of copper after the 1 hour preheating with the butt. So it's reaching 745. And then this is the final temperature of the new anode after 10 minutes of preheating. So I'm reaching a very high temp surface here of 624 after only 10 minutes, because I have this higher conductivity of the contact, and also I have a more conductive material, the copper. And that's to finalize the cycle. That this is the temperature of the block of copper. So it is 674, back to 674. So that's why after that you have pseudo steady state. Every cycle will be at the copper block will come back to that temperature. The end of the cycle, beginning of the next cycle. Okay, third case, I'm replacing my block of copper by a plate of copper. So much thinner, less thermal mass. It will have two impacts. It will react faster, especially in the second part. Will cool down much faster, but it will start with a higher temperature because the system will equilibrium of the first part of in the first step, the mass being less for the copper, the equilibrium of the system it will be at a higher temperature. So now the 660 was not a good starting point for those cycles, because eventually that it's 734 is the final. I'm going to show next the evolution of the temperature of the copper plate from cycle to cycle. So starting at 660, but reach 735. Okay, now, so I will present the last one. So that's the initial temperature of the system, and anode butt placed on top of a plate of copper at 734. After 40 minutes, that's the temperature of the plate, now much higher, 840 both. But so it's higher temperature, but it will cool down much faster because it's a less thermal mass for the second step. So this is after only 2 minutes, this is the temperature on the bottom face of the anode. So it's about 640. So there's two issue with this very fast response. After that's optimum temperature after 2 minutes, but if you wait longer, then that's the temperature, the bottom temperature is dropping because the plate is cooling fast. So now that temperature is dropping back. So that's mean the timing of the event for the anode change will be very stringent. It will be, for operation, it will be very difficult. And also there's a risk of having a thermal shock. And if the new anode may crack because you're trying to preheat it too fast. This is showing the last part, just that to show that we are back, the plate is back to the initial temperature. So because we are concerned about that, we will change that heat transfer coefficient. But before I'm summarize the result, here I achieved 618 degree for the bottom face after only 2 minutes of preheating, and then that's so I kind of explained this. So we are a bit concerned that it is a bit difficult for operation, and there's a risk for cracking the new anode. So now we will replace that number. So we are removing the thermal metal and coming back to a dry contact at 225. And then here I'm presenting directly the result after the 10 minute only Now we are back to 10 minutes of preheating to achieve the maximum temperature. But that maximum temperature is back to 530. So that's the solution after those 5 minutes. 10 minutes, I mean. So now I'm going to summarize. So this is a two-step, and then here I'm presenting all the results in one table. And what's important really is that the type of material and the thickness of that material affect the optimum preheating time for the second step. But the actual optimum temperature or maximum temperature reach depend really on the transfer coefficient of the contact. At 225 is about 500 degree. At 800 it's about 620. So in conclusion, we have done in the morning work in ANSYS to develop this two-step concept. We have tried 3 configurations, and we are hoping that this new idea will make it more practical for trying to attempt to achieve this kind of preheating in real smelter. Thank you very much for your attention.